Howdy, it's Tubalcain again, and in this edition of Machine Shop Tips entitled Introductions to Gears and Gear Cutting, I'm going to talk a little bit about the different kinds of gears and the gear nomenclature and gear formulas and all the related information that is really necessary for you to know, to learn about, and to study before we get into the next few chapters, which will deal strictly with the cutting of the gears. In an upcoming chapter, I will be cutting a gear rack, and a gear rack is nothing more than a straight or a linear gear, and they can be cut on the Bridgeport, but only very, very short ones, like I will show you in the video. Longer ones, of course, have to be cut on a horizontal type of milling machine. Bevel gears are pretty common gears, sometimes called miter gears, and you will be able to cut these on a Bridgeport with special equipment and special cutters, but it's probably not something the average home machinist is going to do. Here we have a large angular gear with the smaller gear. Remember, the smaller gear is often called a pinion, such as the rack and pinion. These are called internal gears or ring gears, and there's a complete planetary gear system. These are helical gears. They run so much quieter than common straight tooth or spur gears, but it's not something you can do at home. This is an interesting type of gear called a herringbone gear. This one is very large, 6 feet in diameter. Again, something that you can't do in your home shop. These are worm gears. Actually, this is the worm. These are very large compared to a man, and this is the worm gear or the worm wheel. They reduce the speed greatly, but again, you can't do this in your basement shop. These are common spur gears. Now, spur gears have the teeth straight across. And this is the type of gear that you can cut on your Bridgeport mill. Of course, you need a dividing head and special cutters, which I'm going to talk about here in a minute. But you notice that these gears have different size teeth, and that is the pitch of the gear, or the diametral pitch. I'm going to cover that too. The interesting thing is that the way that I'm going to show you to cut gears here on the Bridgeport is not the way they're cut in industry in mass production at all. It is really a rather slow process. It would be used in a machine shop to make replacement gears, or one of, or by you guys in your home shops that are possibly making some lathe gears, and I will show you how to do that in some upcoming chapters. Gears are mass-produced and cut in industry with a cutting tool called a hob, and it's done on a hobbing machine, not a milling machine. You might find some interesting YouTube videos on that if you want to study on that, but that is the way that they are mass-produced. Certainly not by this method that we can do in our own shops. In order to cut gears on your standard Bridgeport milling machine, here's what you need. You need a dividing head of some sort, and I have shown you several different kinds. Possibly a tailstock, depending on your setup. And you most certainly need the correct cutters, which I'm going to talk about in a moment. And then you need an arbor to hold the cutters in the vertical position, and these are available with a straight shank, and this is a 3/4 straight shank, or an R8 shank. They'll fit directly into the spindle. And the diameter of these is either 1 inch or 7/8. That is, the arbor size to hold the cutters are 7/8 or 1 inch, and these are 7/8 cutters. That's probably the most popular size bore in these gear cutters. This, of course, could be homemade, but it's preferable to buy one because they're only about $40. This is an 1850 gear cutter, probably made by Brown & Sharp, they say. But most interesting, And look at that dividing plate. This is a dividing head. Can you see the little holes? The hole circles. And up here is the chuck, and then you can see the gear cutter there. So that's where the actual cutting took place, right up here. And the work held in that circular chuck. I can't get any closer to show you that. And mounted on a rather elaborate ornamental type of base. Let's talk about resources and where you can find information on this besides the internet. Some of these old catalogs here, and I like these Boston Gear catalogs. You still find these around. There's quite a bit of good information in these, and several of the pictures that I took or I showed you a little while ago came out of this older book, not any longer available. It's quite old. But Machinery's Handbook, regardless of what edition you have, has a very large section on gears. And matter of fact, starting here on this page, there are approximately 200 pages on gears, and quite a few pages just on spur gearing. So that can be one of your major resources. In addition to that, this is a very good book called Gear Cutting Practice, and you can get that on eBay or maybe even download it. I paid $4 for this book, but there's a lot of good information on gears and gear cutting here. I've shown you this before on Cincinnati Milling Machine Company, and that of course is the dividing head that I'm going to be using. And this information in here tells you how to cut gears and how to use the dividing head, so that's a good resource. And there are just any number of standard machine shop books that you can find, either new or used, that cover gears, gear cutting, dividing, and so on. So be sure and look at some of these resources here, because they are very valuable and worthwhile. In these videos, we're really only interested in cutting involute spur gears with a 14.5 degree pressure angle. And in the reality, often you will have a drawing that will tell you exactly what diameter to cut the gear, how many teeth, what the diametral pitch is, and possibly even what cutter to use. But in case you do not get that on your drawing or your specifications, I'm going to show you how to determine all of that information. And along with that goes some of this terminology that we need to cover. And I'm going to only cover part of it. There's much more than what I will show you, and you can certainly look that up and read about it in the resources that I have shown you. But in reality, much of that information is engineering information and may not be needed at the milling machine. But when you look at a gear like this, you can count the number of teeth, and often the number is stamped on there. For instance, this is a 44, but we need to know the outside diameter because we have to turn the gear blank to whatever diameter is necessary, and it must be very precise when you make your gear blank. In some cases, it's easier to show you this on a toy gear, but there's two circles drawn here that I drew on it, and the outer circle is called the pitch circle, and it is simply the curve of intersection of a pitch surface of revolution and a plane of rotation. According to theory, it is an imaginary circle that rolls without slipping with the pitch circle of a mating gear. Now, is that clear? And the inner circle is called the root circle, and it is tangent to the bottoms of the tooth spaces in a cross section. I don't really expect you to understand that, but the pitch circle is an important circle. Now here's a good picture out of one of these real old books. You need to know what the addendum and the dedendum is. The addendum is the distance from the pitch circle to the outside diameter, and the dedendum is the distance between the pitch circle and the root diameter. And that's why I just gave you those diameters on that toy gear a moment ago. The circular pitch is the distance from the center of one tooth to the center of the next tooth, and circular pitch is the same as linear pitch on a gear rack. When we're cutting, we will cut to the hole depth, and that can be found either by formula or it might be indicated and marked on the gear cutter. That's the hole depth. But in fact, the gears do not mesh all the way to the bottom, and that's called the working depth. There must be a little space left so that there is not too much wear or noise or clashing, and that is the clearance, the little space that is left. There is the thickness of a tooth. Now there are many other terms and a great deal of terminology that I am not going to cover, and I don't think it's necessary for you to know when you're cutting a common spur gear. Probably the most important term of all, and I haven't mentioned it yet, is the diametral pitch. And that is the number of teeth on the gear per inch of diameter of the pitch circle. And it will be sometimes indicated by a DP for diametral pitch, but most often just a P. On this gear cutter, notice that it's the number 4 cutter, 12P. Well, that's 12 diametral pitch. Not all of these gears have the same diametral pitch. Notice that this gear will not mesh with this one or with this one, whereas these two mesh and they are the same diametral pitch. So when you see the teeth that are different size, that's what it means, is that they're a different diametral pitch. So you must match up your gears if you are making gears or replacement gears so that they will have the right pitch and will mesh with one another. If we need to make a replacement gear and there is no drawing, how do we determine the diametral pitch? Well, most all of the catalogs have a page with silhouettes. This is the Boston gear catalog, and you merely match the gear up with the silhouette until you get one that fits. There are also gauges for this that are available. This company, Chicago Gear Works, has the same thing, and the small gears are way here on these little inner circles, and the numbers you see are the diametral pitch. And in this other catalog, they go on for pages as the gears get larger to determine diametral pitch and other dimensions. But there's another method, mathematical, and it's quite accurate. Take this gear for instance. It is 40 teeth that's marked on it, but not all gears will be marked. If not, count them up and be very accurate. Do it twice. So we take that number, and then we also measure it with a micrometer or a caliper, and there is my dimension. It slipped just a bit. I'm just a couple thousandths off there, but it won't matter. Then using this formula for 40 teeth and the diameter below it, P or DP equals the diametral pitch is N plus 2 over D. N is the number of teeth, D is the diameter. And if you work that out, that's 40 plus 2 over the diameter. Simplify it, 42 over 2.332. Divide that out, and we get 18.01, and it was carried out even farther than that. But forget about the change. That is an 18 diametral pitch gear. Next, I want to talk about gear cutters. There are 8 gear cutters in a set of cutters for each diametral pitch. Well, why are there so many, and why do we have to go to that expense? And they are expensive. Because the shape of the teeth vary, starting with a gear. A very small gear has, which we sometimes call a pinion, has teeth that are quite curved. And as we approach larger gears and then all the way up to a rack, and this is a rack here, which is a straight gear, their teeth are almost trapezoidal or straight lined. And all of the other cutters gradually change from this straight line to curve, to a little bit more curve, and so on. And that's why there are so many cutters in a set. In this page from a very old Brown & Sharpe catalog from the 40s, here are the cutters that they sell in any given diametral pitch from a number 1, 2, 3, 4, 5, 6, 7, 8. You can see that a number 1 allows you to cut large gears from a 135 teeth up to a rack. A number 4, for instance, allows you to cut gears with teeth anywhere between 26 and 34 teeth. And as we advance here and get all the way to a number 8, notice that that cutter is only capable of cutting 12 and 13 tooth gears. So depending on the job, you may not need all of these. You can purchase or obtain just the cutter you need for that particular job, because these are pricey, sometimes $50 and more each, and you can buy them either individually or in sets. In fact, what I just told you a moment ago was a bit of a fib, because there are actually 15 cutters in a complete set, but I don't believe they do that anymore. But in the case of what I told you moments ago on that other page, some of those cutters were only an approximation of what you really need. So you can see here, if you want to study this, that these other cutters are kind of in between and allow you more exact gear geometry. That's free of charge, and you probably do not need to know that. Actually, because of the cost of these cutters, old Tubalcain himself doesn't even have full sets. But I have some common ones here that can be used, and I will be using these in demonstrations. But let's take a look at what it says on an individual cutter. This is the number 4 cutter in a set, 12 diametral pitch, and it will cut anywhere between 26 through 34 teeth. And the 180 there is the depth of the teeth. So you would write that down, of course, before you start, because once it's mounted on an arbor, you can't read it anymore. It's hidden. And on the back side, there's usually some other information, such as keep it sharp. It's made of high-speed steel, and it was made by Brown & Sharpe. And examine the cutter. This is a form cutter, to make sure it's not dull or chipped. Now these can be resharpened at a tool and cutter grinder, and all they do is grind the end here, so they don't change the form of the tooth shape. Most of these cutters are approximately 2 inches in diameter, and you need to know that, or remember that when you set your spindle speed, that you're actually dealing with a rather large cutter. So you have to slow it down, especially if you're cutting steel or harder materials. And you need to know the bore size. Mentioned previously, this is 7/8. And one other thing that you might need to know, and write it down before you mount it, is the thickness of the cutter. So check it with a micrometer right here, the thickness, and they vary. None of them will be the same. The reason you need to know that is that when you go to set your cutter on the center line of your arbor when you're cutting it, you might need to know that dimension, or half of that dimension, so that you can find your center. There are rules and formulae for the dimensions of spur gears, and this information is available in many different books, or in Machinery's Handbook. And another excellent book is a booklet put out by Cincinnati Milling Machine Company, and I used it when I was teaching and as a student, simply called Cutting Spur Gears, and it is available on the internet as a download, I believe, from Vintage Machinery. But here are the formulae that you probably need to know. Many more are available, because sometimes what your givens are not the same. So diametral pitch is simply number of teeth over the diameter. There are other formulas for that. Often you need to know the outside diameter, and that equals the number of teeth plus 2 over the diametral pitch. The hole depth is usually given to you on a cutter, but if it is not, use this formula, 2.157 over diametral pitch, and you can find the hole depth, and that's strictly for a 14.5 degree pressure angle. Now if you want to know more about pressure angle, you're going to have to read up on it, because it is incredibly complex. And finally, to determine the number of teeth, it's diameter times diametral pitch. That will get you started, but be sure and read through all of these books that I have recommended. And that concludes this video on spur gears, and much of what I have just told you will be used in later videos where I cut spur gears by several different methods on the Bridgeport milling machine, so be sure and watch those other videos. And this is Tubalcain saying so long for now.